Stand at a busy intersection, and it looks like a study in pure randomness. Cars weaving, pedestrians darting, and trucks braking at the last second. In business, whether managing global logistics or a trauma center, daily operations often feel exactly like this. To try and tame this unpredictability, most people reach for a familiar tool, the average. They calculate the expected value over a given period and build their entire strategy around that single number. But averages hide a glaring logic gap. Imagine a city planner analyzing that dangerous intersection. The data shows an expected value of 3.5 accidents per week. The math gives us a clean number, but you cannot have half a car crash. Reality doesn't operate in fractions of an event. If a hospital staffs their emergency room anticipating precisely 3.5 accidents every 7 days, they risk being overwhelmed. They might see 0 accidents from Monday through Thursday, and then face 5 severe crashes on a Friday night. Relying solely on that weekly average obscures the actual daily volatility. This is where we need a mathematical upgrade. Discrete probability distributions allow us to move beyond flat averages by mapping out the specific odds of every possible outcome. Instead of guessing at an average, we can calculate the exact likelihood of every scenario, from a quiet day to a total surge. Before we can map these outcomes, we have to establish a ground rule. We are dealing with discrete variables. These are distinct events we count in whole numbers, like the number of defective items in a batch, or the number of children in a household. We aren't measuring a sliding scale, we are counting occurrences. Take a specific business scenario. A financial institution receives a new batch of exactly 25 car loan applications to process. Management knows their historical baseline. Over the past few quarters, they'd have approved 70, but what happens when the binomial tool just doesn't fit the reality of the situation? Consider the chaotic environment of a customer service call center. Here, the binomial distribution is useless because there are no fixed trials. We don't have a neat stack of folders. A customer could dial in at any given millisecond, making the occurrences entirely open-ended. The center's historical data provides one parameter. They receive calls at an average rate of 8 per minute. Again, the average isn't enough to run the floor. Management needs to calculate the odds of a sudden surge. What is the probability they will receive exactly 20 calls in the next 60 seconds? For this, we reach for the Poisson Distribution. This calculates the probability of events clustering over a continuous interval, like a window of time, a stretch of distance, or a volume of space. This chart shows the Poisson probability density function for a scenario with 12 occurrences on average. Notice how they cluster predictably around that value. The formula calculates outliers, mapping the exact probabilities as occurrences push toward rare events like 20. Poisson provides the mathematical odds of extreme surges or total lulls over a defined interval. It gives management the foresight to adjust staffing before the phone lines ever start ringing. Navigating uncertainty requires asking the correct diagnostic question about the boundaries of your data. You must identify the rules of the game. Are you working within a strict limit of fixed trials? Or are you measuring an open-ended rate over a continuous interval? Applying the correct distribution clarifies data across industries. We use these models to anticipate errors in data entry, the number of vehicles sold per day, or the frequency of factory machine breakdowns during a night shift. While events often look erratic in the moment, these distributions demonstrate that they follow clear mathematical patterns when viewed over hundreds of instances. Data scientists utilize these discrete distributions to quantify uncertainty. By mapping these probabilities, they turn guesswork into a set of calculated, actionable risks.